Okay. Hi everyone. So my name is Yizhou. I'm a graduate student from ICME and Stanford. So today I want to talk about mainly the applications of deep learning based methods to spatial interpolation of nearshore bathymetry with sparse measurements. So bathymetry refers to basically the depths of water in areas such as ocean, rivers, lakes, or streams. So it's mostly important because of shipping operations, risk assessment, and also military operations. However, so usually it's relatively difficult to obtain bathymetry with high resolution directly because of sometimes budget constraints or logistical restrictions. So usually there are some indirect approaches to estimate those bathymetry to obtain some kind of high resolution mapping, including remote sensing based methods and also spatial interpolation methods. So today I want to basically talk about how we can apply deep learning based methods to spatial interpolation. And also I will compare it with Kriging, which is one of the most widely used stochastic methods for spatial interpolation. So basically I will apply our methods by using point-wise sparse measurement of nearshore bathymetry as input, and eventually make a prediction of the overall high resolution bathymetry. I will compare our methods basically based on two most important aspects. The first one is the prior information that each method is assuming. And the second one is the eventual error that each method seeks to minimize. So essentially these two aspects represent the two most important information we are using for our problem. The first one basically assumes what we already know about our data other than the observation we have. So basically we may assume our data has some kind of Gaussian distribution with certain variations, etc. And the second one, the error to minimize, essentially determines the kind of type of solutions that we eventually want to have. So different types of error eventually will give us different solutions with different properties that we may want to have in the end. So first I will talk about how Kriging uses the prior knowledge. So basically Kriging assumes its knowledge in the forms of a semi-variogram, which basically describes how much our data points varies as a function of the distance. So we may assume that our data maybe have some kind of Gaussian distribution such that our covariance follows certain function, for example, maybe spherical, exponential, or some other distance functions. And we pass this semi-variogram into our Kriging-based methods along with our observations to make our eventual posterior estimates. So this is the first aspect, and the second aspect is that our Kriging essentially is the best linear estimator that minimizes our mean squared error. So this is important because usually this gives us smooth solutions that minimizes solutions point-wise. So essentially, this is one of the possible reasons it will give us solution that might not have what we want, such as maybe some solution with sharp boundaries. So the second method I want to talk about is deep learning based methods. So in this, in our framework, we are using training data. So deep learning neural network is using its training data as its prior knowledge, as its assumption on the data that we want to estimate. And so we may, for example, sample from certain distribution that we assume and essentially use this as a training data for our deep neural network. So after this is trained, we assume that deep neural network has learned enough about the prior knowledge, and essentially it just given the input or our observations is going to give us the final estimate. So in this case, we are passing some rectangular jumps in our training data. Hopefully we want to use this to represent some kind of solution with sharp boundaries, so that hopefully the deep neural network can do a better job when the input are from solutions with, such as, for example, sharp gradient components. And the second thing is that our deep neural network can minimize the mean square error or the mean absolute error. So when the deep neural network minimizes the mean absolute error, it actually does not, it has a higher allowance for error for solutions with sharp boundaries, because usually this will give us a better solution in terms of smaller mean absolute error. But so basically the mean square error also has another, so there's a second perspective for this one, which I will talk about in terms of a mathematical point of view. So when this is basically a well-known mathematical statement, which is basically when we try to estimate our observation, in this case is our y is our observation, and when we try to estimate our x solution, and when our estimator minimizes the mean squared error, it's going to be equal to the mean or the average in our posterior distribution. So this is basically how we can explain why deep neural network might potentially do a better job, because when we train our training data, which is from x1, y1 to xn, yn, and take the average of the mean squared error, we're essentially trying to find a minimizer that are close to the average in our posterior distribution. And we can even show that when we increase the number of samples, assuming we find our minimizer over all deep neural networks, the eventual estimator will converge in probability to our posterior average. So now I will talk about the application of this deep neural network framework. So our data consists of monthly nearshore surveys taken at the FRF Field Research Facility at North Carolina and USA. So it's basically a rectangular measurement domain, which consists of 900 meters across shore and 1,200 meters along shore, with around 3,500 measurement points. So this is a sample of the nearshore bathymetry. And so we have 265 monthly surveys in total. And so we are using 240 surveys out of 265 as our training data. And for each survey, we generated around 40 training samples by adding some kind of Gaussian variation and also sharp gradient component. And eventually we have around 10,000 training samples for our deep neural network. And so this is a comparison on the result, which is one of the 15 monthly surveys not included in the training sample. And as we can see here, deep neural network has a overall better prediction, as well as a lower mean squared error. So this is a comparison of the overall 15 FRF surveys outside the training samples. So we can see here, the deep neural network actually has a consistently lower error in terms of its prediction than Kriging. This is a example of a monthly survey with some added sharp gradient component as a comparison for Kriging and deep neural networks. So as we can see here, deep neural network has a prediction with lower mean absolute error, as well as a solution prediction with sharper boundaries. So I have also plotted the across shore section as well as the along shore section of the predictions. And as we can see here, so Kriging actually gives us a smooth solution near the location of the sharp jump, whereas deep neural network has a much sharper boundary near the location of the jump. So this is the first reason that caused this phenomena is that, so basically the deep neural network has a better prior knowledge in terms of its training data, because that we have actually added those training samples with sharp gradient component when we train the deep neural network, whereas the Kriging basically assumes a general distribution of Gaussian in terms of prediction and in terms of its prior knowledge. And the second reason is that because the Kriging actually tries to estimate the mean squared error. So when it gets to predict the points near the location of jump, this kind of smooth transition actually gives us the minimizer of the mean square error. Whereas when our deep neural network tries to predict a solution that minimizes the mean absolute error, we actually allowed it to give this kind of prediction with much sharper boundaries. Second, I want to mention that it is also possible to combine deep neural networks with Kriging, in the sense that we first pass our sparse measurements into deep neural networks to obtain our first step estimation. And after we obtain this, we can actually subtract our estimation at measurement points from our original measurement to obtain the residual from our deep neural networks, which can be further passed into our Kriging to actually predict the overall residual. And we can actually improve our estimation by adding this estimate residual back into our deep neural networks. So this is actually assuming that when we make predictions using deep neural network, the eventual residual from our deep neural network actually has some kind of spatial correlation, so that it can actually be estimated by our Kriging method. So eventually this estimation can further improve our prediction made by our deep neural networks. So this is a illustration, a comparison of the methods using also one of the 15 surveys not included in the training set. So as we can see here, the neural network residual Kriging actually has a better performance than both of the methods. And I also want to comment that one of the reasons is also that it actually resembles to some degree the structure of residual neural networks, which is possibly why it may have a better performance. And so lastly, I want to show another perspective. So previously I have shown that using deep neural networks to directly estimate our bathymetry when we use the mean square error actually are approximating the mean or the average in our posterior distribution. And so the second approach in this case is actually we can use deep neural network or a conditional generative adversarial network to directly obtain some kind of distribution, posterior distribution, by using a generator and a discriminator. So in the framework of a conditional generative adversarial neural network, we actually has two most important components. The first one is the generator, which takes a noise and it's also some kind of label. In this case, is our observation, and they eventually generate some kind of sample or bathymetry sample. And the discriminator is going to take these fake samples generated by our generator along with the real samples, eventually to try to discriminate which one is real or which one is fake. And so we train these two neural networks, the generator and also the discriminator, in an adversarial manner, so that eventually we hope the generator will generate samples that are as close to our real sample as possible. So it actually has been shown that when we train our neural network in this manner, when we use our label as some kind of observation from our data, the neural network can eventually generate approximations of the posterior distribution in a mathematical perspective. So in our case, our data are actually using the grid cell average and also point-wise measurement as our measurement and or our label into the generator, along with some noise. So eventually it's going to generate bathymetry on the top right as a fake sample, so that eventually, hopefully it will be as close to real sample as possible. So this is also a comparison of the 15 surveys not included in the training data. So as we can see here, so we are making predictions from our conditional generative adversarial neural network by taking the average over sampling from our generator. So let me go back. So essentially, when we have some kind of observation, we pass it as a label into our generator along with our noise to generate a certain number of samples. For example, maybe 100 or 10,000. 1,000 samples, and eventually we compute the average over those samples as hopefully the average over in our posterior distribution as our final prediction. So here is a comparison of the overall prediction on 15 surveys not included in the training data. As we can see here, cGAN also gives us a better overall prediction than Kriging in terms of root mean squared error. And so this is a comparison specific on a specific monthly survey with some added sharp gradient component. So as we can see here, the conditional GAN has a prediction with lower mean absolute error as well as a much sharper boundary. So I guess this one is actually, we have the explanation will be close to before in terms of prior knowledge. So because the conditional GAN is trying to approximating the posterior distribution from our prior distribution that consists of training samples with added sharp gradient component. So it naturally is going to predict or give us an approximation of posterior distribution with also very sharp boundaries as shown here in the alongshore section. So on the other hand, so Kriging, which only has a very general assumption on the distribution of data, it only gives us a smooth solution, and also because of it's minimizing the mean squared error. That's also possibly the other reason why it's giving us this smooth transition near the location of the jaw. So to conclude, so we can use deep neural network to make better or more accurate predictions when we have a better prior knowledge in terms of our data. And when we use a fully connected deep neural network, we can directly approximate the mean or the average in the posterior distribution. And when we use the conditional GAN, we can actually try to approximate the posterior distribution directly through our generator, and also sample data through our generator. And we can also possibly combine deep neural network with Kriging to potentially give a more accurate result. So for working future, hopefully we will use more realistic physical shapes such as sandbar structure or rocks to represent components with sharp gradient or sharp changes, so that eventually it will have a more realistic application.
All right, great job.
Yeah,
oh, that's more. Okay. Well, thank you so much. That was a great talk. Open the questions up. Anybody on the chat or want to jump in?
Hey, Yizhou. Can you just slide about cGAN result? Just wonder, you plotted the cGAN, yes, this one. Is it only one realization or average of realization from cGAN?
This is 100, the average over 100 realization.
Okay, I see. And another question about this neural network, Residual and Kriging. So did you have just one iteration of the alternating two method and to get the performance performed than the others, or just you need many iterations?
I try to do more than one iteration, yes, and so usually it gives me better result maybe in 2 iteration or 3 iteration, but afterwards usually the results are going to be worse. Yeah.
Yeah. Do you have any proof or some kind of the confirmation that it will converge to some sort of the optimum, like local optimum?
I haven't looked through that. Yeah, I'm afraid I haven't thought very carefully about that. Yeah.
Okay, thank you.
Can I ask you, this is Matthew, real quick. Can you remind me, did you apply the NNRK to the sharp gradient problem or just the real bathymetry?
I applied, so since we are when we use Kriging to apply the residual, so it's also going to have this kind of smooth transition problem. So when you have a prediction of the deep neural network for solution with sharp boundaries, usually it's also going to have this kind of sharp transitions in the residual. And that is why when we use Kriging to estimate the residual, it actually gives us not very good results. Yeah.
Any other questions? I have one for you. So a lot of this data is, or all the data is based out of the same beach out at the field research facility, which is going to have a similar background slope overall on the data set. So if we look to expanding this to other locations or other scenarios, so how sensitive or how much data do you think it would need to train up to be able to handle that different background slope with a gradient on it?
So right now I'm adding Gaussian variation for each survey, but yeah, I think to extend it to more general nearshore bathymetries, I think we will actually need much more data than just 240, and so basically when we only, so actually those monthly surveys do not have much variation, which is why I'm adding the Gaussian variation to make the overall training sample to have more variability. And so I think if we want to extend it to more general nearshore bathymetry, we will need a better generalization other than the just Gaussian noise, I guess. Yeah.
Okay. All right. Well, unless there's any more questions, thank you so much. And that concludes day 2. So we are back tomorrow morning at 9 a.m. Pacific time with a little shorter day, but some really good talks tomorrow. So thank you all for being on the call all day today and participating, and we will see you tomorrow morning. Thank you very much.